Okay, now what we want to look at is what we call a limiting sum of geometric progression. Now, geometric progressions can go up and sometimes they get really large, but sometimes they can get really small. The sums can not be getting too big because the terms start to be getting smaller. So let's have a look at this poor little problem. This problem here of poor little Froggy. We've got Froggy wants to jump across a pond that's 1 metre wide. The problem that he has is that he can only jump half the distance of what's required to jump to the other side. So will he make it? Okay, here's a little frog here. If you find out his name, let me know, because he's got a special name. So there's a challenge. So his first jump, see, he can only jump 50 centimetres. His second jump, he can only jump half the distance of the previous one, which would be 25 centimetres. The next one would be only half the distance again, so 12.5, then 6.25, then 3.125. If we start to add this up, we can see it's getting closer to a metre. But if we keep adding, we're going to find that we're getting close, but we're not going to get close enough. He's not going to reach that metre. He's going to get close because he keeps jumps half the distance that he needs to. But because he can only jump half the distance that he needs to, that means he can never get there. So that's what we're going to call a limiting sum, because it gets close to a particular value, but it never actually reaches that value. So what that's where we get the idea of a limiting sum of a GP. It gets close, but never gets there. So let's have a look at some of these. Well, let's have a look at the formula first, and then some questions. So the formula we're going to use this time, a little bit simpler, A on 1 minus R. So we've got that. And then if you've got, this only works if we've got the ratio between -1 and 1. So you've got to have that ratio between -1, because you're relying on your terms getting smaller and smaller. If the ratio is greater than 1 or less than -1, the terms are going to get, in absolute value terms, are going to get really large. So that's not going to reach a limiting sum. The idea of a limiting sum is that the terms get closer, that all the sum gets closer and closer to a particular point. And that only happens when you're a fraction. So you need a fraction every time. It won't work unless it's a fraction. So if we have a look at our limiting sum, this one, 10, 5, 2.5, ratios are half. The first term's 10. So if we substitute into our formula, A over 1 minus R, we're going to get 20. And you can see that it's getting it close to 20. 10 plus 5 plus 2.5 plus 1.25 and so on. It's going to get close to 20. Won't actually reach 20. So the sum's not actually 20. It's what we call a limiting sum. The actual sum, it keeps going on forever. It's a sum to infinity. So it's going to get close to 20, but the terms are going to be really small, and then we're going to keep adding smaller and smaller terms, so it never actually gets there. So in 2, our series is a little bit different because we've got a negative series. We've got a negative ratio because it goes 60, 30, 15. So if we start to have a look at our ratio here, when we start to add them up, 60 minus 30 is 30. We add 15, we get 45. We subtract 7.5, we get 37.5. Add 3.25, we get 41.25. So we're seeing that it's starting at 60 and then going down to 30, up to 45, 37.5. So it's oscillating around a particular point. So this one's a little bit interesting that when you've got a negative ratio, it doesn't actually go up to a particular point. It circles around a particular point and hones in on a particular number. Then that would be our limiting sum. So applying our formula here, 60 for the first term, minus a half for the ratio, substituted in A on 1 minus R, we're going to get 40. So you can see that this series was getting closer to 40. It's got getting closer and closer. It's not there yet, but it never actually will get to 40. It'll be above and below 40 all the time. So it'll just get closer and closer to being above and below 40. So really small numbers, differences between 40 and the sum, but it will get closer and closer. A problem here, we've got a tree that starts off at 3 meters, and then every year it gets 1/3 taller than it was the previous year. So in its second year, the 1/3 of 3 gives us 1. So then next year, it grows 1/3 of a meter, and then 1/9 of a meter, and 1 on 27th of a meter. So it's getting bigger, but it's the rate at which it gets bigger is decreasing. It's slowing down a lot. So the ratio there would be 1/3. Our first term is 3, and our sum would be A on 1 minus R. We sub it in. We get it's going to get to 4.5 meters. It's going to get close, but it's not going to get completely there.